So today I'll finish up talking about wood stoves and then go on and talk about how water, steam, and ice work. See, is it? All right. So I talked last time about how to, in a sense, how to make thermal energy out of ordered energy by burning stuff, the chemical reactions involved in that. And so that's the source of ultimately the heat that the wood stove is going to transfer to the room. The issue now is how does it transfer the thermal energy to the room? And of course, as I hope you notice with all the topics that we do specifically, this generalizes to many other contexts beyond just wood stoves. So the three classic heat transfer mechanisms, and I think they're essentially complete, are conduction, convection, and radiation. And just to remind you, we'll do them carefully in a minute, but conduction is the transfer of heat through a material without the material itself moving. It's through the material. Heat, as always, flows from hotter to colder, so it's going from the hot end of some piece of material to the cold end of some piece of material. And we'll look a little more carefully at the rules that govern that conduction of heat through materials in a minute. Second mechanism for heat transfer is convection. And this is heat being transferred in the movement of material. So, for example, in a liquid or a gas, I mean, I guess that's complete too. Solids don't move around much. So convection is heat that goes into a fluid like gas or liquid. Then the fluid itself moves and delivers heat to a colder location by going there. Again, it's going from hotter to colder. Radiation is the more exotic one. This is heat transferred from one object to another by way of electromagnetic radiation. And electromagnetic radiation travels through empty space. It doesn't need any context through which to travel, no material. They looked a bit over a century ago, people were struggling to try to figure out what electromagnetic waves traveled in. It turns out it doesn't travel in anything except empty space. It's not ripples on an ocean of water or sound traveling through a room full of air. They're just traveling through empty space. And they convey heat, again, from hotter to colder. So now we have to look more carefully at those three mechanisms. So the first one is conduction. And in the wood stove, it's present in many places, but it's particularly relevant for the movement of heat from inside the stove to outside the stove. And a value of this, the fact that heat goes from the hot burning stuff inside the stove to the surface, the outer surface of the stove by way of conduction. Nothing is moving through the stove to get to the outside, so you leave behind all the smoke and whatever, the ash and so on. It stays inside. The heat gets out, but none of the materials get out. And so in that sense, the wood stove is acting as what's known as a heat exchanger. And heat exchangers are all over the place. What is a heat exchanger? It's a device that moves heat from a hotter something to a colder something without moving the somethings. An example of this is, so the wood stove, it's taking heat from inside where the burning is going on to outside where the room air is going on, but no transfer of material. Another one that's going to come up in the near future is air conditioners. They also move heat. Typically, it's from your room air, which is hot, into a working fluid, which we'll find inside the air conditioner, which is cold. The heat goes through the wall of a piece of aluminum. Your room air doesn't go into the air conditioner. Just the heat from the room air goes into the air conditioner. So it's a heat exchanger, and they're useful for things. In fact, one other place where it should show up, but it doesn't particularly. It's rarely seen. Modern houses, many of them are so well sealed that the air inside the house doesn't turn over very fast. Old houses, they turn over all the air in the house every hour or two or three. So if you could paint all the air molecules in your house red and wait an hour or two, there wouldn't be very many red molecules left. They would have exchanged the outside, drifted out. That's energy inefficient. If you're losing a lot of air in and out of the house, you're also losing a lot of heat in or out of the house, and it's hard to then keep your house atmosphere controlled the way you like it, right humidity, right temperature, all that. So modern houses, a lot of them are sealed, not like not hermetic seal where nothing gets traded, but they get pretty seriously sealed, and so all the the air doesn't move back and forth, but so do, all the smells and stuff that you don't particularly like to have lingering in your house get sort of trapped in there. So how can you solve this problem? Well, it should be possible to send the air from the inside out and from outside in, but you want to trade off the heat that one has and the other doesn't. So for example, on a hot summer day when your room air has been beautifully chilled by an air conditioner, you don't just want to send that nice cold air outside and bring in hot air from outside back in. You don't want to swap. That's not a good trade. That messes up the coolness of your house. So what do? On the way through that transfer, let them exchange heat, not material. Just pass heat through a wall of something and allow them to, the cold air going out draws heat from the hot air going in, and what arrives outside then is hot air from inside. And what arrives inside is cooled air from outside. I hope that's vaguely followable. Anyway, so heat exchangers are around and they're important. We have them in our bodies. I'll do one more of these. Your blood flowing out to your hand exchanges heat between veins and arteries with blood coming back from your hand. As a result, your hand can get very cold on a winter day, and it doesn't mess up your core body temperature because the warm blood going down to your hand gives up heat to cooled blood coming back from your hand. That warms up the blood as it travels back to your core and cools off the blood as it heads to your hand. So your hand's temperature can drop, doesn't mess you up. So we have that naturally. All right, that's the story of heat exchangers. I'll stop with that one. And go back to this, the relevant one here, which is conduction of heat. How does heat actually manage to go through materials? And the first mechanism for heat actually transferring, if you zoom in on the material and watch its atoms and molecules moving around, they are moving around jiggling with thermal energy. So I picture them as a kind of a busy, in a solid, say a piece of metal, the atoms, the little atomic cores, nuclei and stuff, they're not motionless. They're not going anywhere overall, but they're jiggling in place. And they bump into each other. They're pushing on each other periodically. They have kinetic energy. They have potential energy as they jostle against one another. And it's that mixture of kinetic energy and potential energy that is the thermal energy. It's just sprinkled randomly statistically among the particles. Well, the fact that they're jostling against one another allows them to exchange energy. And if you have one end of the material much hotter in temperature than the other end, and you can do this, you just hold a blowtorch to this side and not to this side, the particles over here will be jostling around more vigorously. They have more, on average, more thermal kinetic energy. They have more of this random motional energy. And so they're jostling vigorously, whereas the ones at the other end are jostling much less vigorously. And there is a statistical transfer of energy. Every time they bump into each other and push, and the other one moves a small distance in the direction of its push, it does a little tiny dose of work on its neighbor. And so the neighbors are doing work on each other back and forth. And if you watch the statistical trade-off, it is statistically likely that heat will gradually move from the hotter stuff to the colder stuff. It's just like if all of you started exchanging dollars randomly. Those of you who showed up here with more dollars than others would gradually lose them. And the ones that people who came in here with few dollars would end up gradually accumulating. You all drift towards the same distribution of dollars. So that's what's going on with heat. The heat is gradually migrating from the particles that have a lot of it, a lot of thermal energy, to those who have relatively little, just out of statistical exchanges, all involving tiny doses of work. Questions about that idea? If you can just picture just this animation of, one day I'll do that, of the vigorously vibrating ones in one place, less so there, and the heat migrates. I think of that as a bucket brigade approach to the transfer of energy. Bucket brigade, for those of you, stuff just drifts out of the cultural lexicon with time. Bucket brigade was the idea of fighting a fire where you're all you line up the whole town, the fire's over there, the river's over here, everybody's passing buckets. And so the heat is flowing from one person to the next like a bucket of water from one person to the next, and so on. For heat to go from one end of a metal, pick any material, from one end of a rod to another, it's going to have to go atom by atom by atom by atom by atom through the whole thing. It's a very arduous process, but it works. And this is the main way in which heat flows through materials that do not conduct electricity. So that's things like glass and plastic, crystals of various sorts, wood, a lot of household material, ceramics. The heat is going by sequential jostling of atom after atom after atom, working its way through. Different materials have different abilities to convey heat that way. Some are better than others. They're all not very good. There are very few materials that use this technique as the primary technique that conduct heat well. One of the rare exceptions is diamond. Diamond is actually a very good conductor of heat, and yet it does not conduct electricity. It uses this bucket brigade process fantastically well. It's almost, it's not quite a unique, but it's among the few. So what's the alternative? The alternative is in materials that conduct electricity, they have something else that can move through them and can carry heat. And it turns out the conduction of electricity in most materials, there are exceptions, materials that conduct electricity do it by way of their electrons. The particles that live at the outsides of atoms. They're very low mass. They form this cloud around the nucleus of an atom, and they're involved in chemical bonding and chemistry in general. And in metallic systems, conducting systems in general, those electrons are not limited in their motion to a single atom. Instead of being stuck around a single atom, they're shared in some respects by many atoms. And so they can move. And for electrical conductors, that means that if you exert forces on electrons at one end of the material, you can cause them to flow through the entire material and come out the other end. And the forces involved usually are electric forces, which is a topic for the other semester of this class. But you can propel a movement, an overall flow of electrons. It's sort of a liquid flowing through the material, and that's how electricity is conducted in virtually all the materials we encounter day to day. Those same electrons that conduct electricity can also carry heat. So if you have a piece of metal and you heat one side, this is why sometimes in the past 10 minutes when I wanted to say about a metal rod, I froze up and wanted to choose a different thing. Because in metal rods, that bucket brigade process is sort of a minor player in the play that is heat conduction. It's mostly the electrons that are doing the job. And they are migrating very swiftly from one end, the hot end, to the cold end, carrying heat with them, and then they go back. They're wandering randomly through the material in the absence of any forces pushing currents through the material, electric currents through the material. But that random motion carries heat. So that if you have electrons on the hot end, they get smacked by something, they suddenly pick up a big dose of thermal energy, and they will travel not just to the nearest neighbor atom and drop off that heat, but they can travel 10 or 100 or 1,000 or 10,000 atoms in a single shot, very fast. They carry heat in giant steps through the material. And actually, the better the conductor, the faster heat flows through it, the more effective conduction becomes. Because the better conductors are the materials that allow the electrons to move better. And similarly, since they carry electricity better, they carry heat better. And with that, then, let me start this demonstration, and I'll explain it as I start it. I'm going to provide a source of heat here at the center of this center hub here, on which are connected 3 metal rods. One rod is copper. One rod is, and I never check in advance, one of them's stainless and one of them's aluminum. And usually I can tell the difference by look, but I'm not sure. After the years and years of use, they both have sort of got the same appearance. So one of them's aluminum, one of them's copper, one of them's stainless steel. Copper is the best electrical conductor of the trio, and it will carry heat the fastest. So as heat flows out these rods, which are started at room temperature, obviously, it will melt wax that is holding metal marbles in place. So we're going to lose first the inner metal marbles, then the next row, and so on to the last one. I would bet I'm not going to bet big money on anything. You never know what's going to go wrong. But, you know, all likelihood, medium money, that ball is going to be the first end ball to go off. Why? Because this carries heat so nicely. So, see, copper finally lost one of its marbles, but so did this one. I don't know what that one is yet. We'll see. So heat flows out through copper very nicely. It's the best conductor of the ones that you can afford. Silver's better, but yeah, silver gets expensive. So, great conductor. It's going to carry heat out to the end, melt that last blob of wax, and drop the ball first. Aluminum is a good second. It's not as good as copper as a conductor of electricity or of heat, but it's pretty good. And so it won't keep pace with copper, but it'll try. Stainless steel, however, is a terrible conductor of heat. So copper's really cooking here. Stainless steel is a lousy conductor of electricity and of heat for a reason that has to do with the structure of the metal. Stainless steel is an alloy. It is not a single element. It's a mixture primarily of iron, but it also has chromium and nickel in it. And the amount, this has to be aluminum. This must be the stainless steel one. So stainless steel. So in here is iron, chromium, nickel, and sometimes they put other things in there. And the exact balance between those depends on which stainless steel you're working with, which is a whole nother fascinating story. But because at the sort of atomic level, stainless steel is a mishmash of different things, the electrons have trouble coasting through it nicely. They keep hitting transitions and defects in the material. And it turns out that the more perfect the structure the electrons are passing through, the better they go. And the farther they travel before they hit something by accident. So anything that messes up the structure of a metal tends to decrease its ability to conduct electricity and heat. So copper won here. Aluminum's getting close. So stainless steel, because it's full of this mishmash structure, is a very poor conductor of heat. And these serve purposes, say, in cooking. If you want the pot to spread heat beautifully around the bottom of your pot and make sure there are no hot spots, no cold spots, you use copper or you use aluminum. Those, however, tend not to be great in contact with food, so what do? Aluminum is pretty good, but it's hard to keep aluminum as clean, say, as stainless steel. So some of the fanciest of cookpots have copper or aluminum at the core to spread the heat nicely, but they decorate it on the outside with a thin layer of stainless steel, which you can keep nice and clean. It looks beautiful and all that for years. It's a terrible conductor of heat, but if you don't make it do that job, you make it keep the thing clean only, you're good. So, I mean, stainless steel hasn't even lost a single marble yet. The other guys have totally lost their marbles, along with the instructor. What else about this? Oh, and so if you want to make a portion of a pot that is safe to hold even when the pot's hot, stainless steel is a good choice. Actually, beyond that, sort of the rules governing the flow of heat. I think I've got a question to ask on this one. Yeah. If you think about just the way in which heat flows through materials, so this question is, which direction gives the most heat flow for a given difference in temperature? So hot versus cold. Suppose they're different by 10 degrees on some temperature scale. Do you want the heat to flow through the thin wall of a wood stove, so from the inside to the out, or along the thin wall of the wood stove? That is, from the left side of the wood stove to the right side of the wood stove, across that face. Which way do you think carries the most heat? And it should not be a hard question. How many think A, it's through the thin wall that you get the most heat flow for a given temperature difference? How many think B, that it's along the face that you get the most heat flow? And how about the two are equivalent or the same? Okay, getting very, 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 very light voting here. Enough that it's in the noise. Like if I did a poll like this, I couldn't even publish it. It is going to be the most heat flow is going to go through the surface from back to front. And the reason for that is the rate at which heat flows through materials is governed by a pretty simple law. First of all, it depends on the material. So there's a constant associated with each material. It's a very tiny constant for something like glass or plastic or ceramic. It's a much bigger constant for something like copper. A lot more heat's going to flow for the same situation. The next thing that matters is how far apart the hot and cold are, and the closer they get, the faster heat is going to flow. Next thing that matters is the difference in temperature. So the bigger the difference in temperature, and the closer those temperatures are, the faster heat flows. And it's a simple relationship. I'm not going to do the details. And the last thing is how much surface area is the heat going to flow through. So if you've got if you've got a surface that's this big, a certain amount of heat will flow in that situation. If you have one that has 4 times as much surface, it's this big, 4 times as much heat's going to flow. It just scales with how much passageway there is for the heat to flow. The most important piece of that is that 2 parts. The temperature difference matters, so the bigger the temperature difference, the faster heat flows. And the other thing is, the closer the hot and cold part are to one another, the faster heat flows. And this is why when you insulate your house, and we'll talk about insulation another day, first off, you don't want to unnecessarily increase the temperature difference between inside and outside. The bigger that temperature difference is, the faster heat is going to flow. So when you air condition your house to suit the polar bears and penguins that you've adopted as pets, and on a super hot summer day, you're going to have a lot of heat flowing in. The inside temperature is very low, the outside is very high. Heat's going to come roaring through anything. But the other part is that you want to have your walls and various other structures as thick as possible. Thicker is better, because you're separating the difference in temperatures by more and more distance. You're reducing conductive heat flow. All right? All right. This stainless steel finally managed to drop one and only one ball. And I know from the past that it never manages to drop the last ball. In fact, it's cool. This is still cool to touch. Even here, that's nothing yet. It's just not going to happen. So, any questions about conductive heat transfer? Things you're wondering about with it? All right. Convection. So convection is the movement of heat in a fluid. The wood stove uses conduction to get the heat to the outside surface of the stove. So that outside surface of the stove is nice and hot. And now the heat's got to move into the room, and one of the ways it moves is by way of convection. And convection involves heating a fluid up through contact with a material, with a hot surface, and then having the fluid move. And the fluid, here on Earth, the fluid will move spontaneously just because of the buoyant force. And I showed you this a little last time. I'll show it to you more. Turn that off. Turn this on. And dim the room lights. So what you're seeing over here is an image projected of a metal filament, like from an old-fashioned light bulb. And we're going to run an electric current through it, and that current will heat it. So it's going to become hot. It'll be the hottest thing in this little container so there's a little container of water here. That's the top surface of the water projected up here, and the rest of this area that you're seeing here projected, you're looking through the water. So I'm now going to start heating the filament, and I hope you can see rising from that filament filaments of heated water. It's being lifted by the buoyant force. The water was at room temperature. Where it comes in contact with that hot filament, it's several degrees above room temperature, and its density decreases and it gets lifted. It's lighter than the surrounding liquid, and it gets lifted by the buoyant force to the top surface. You see it up here hitting the top surface basically and spreading out left and right. And as it does, it gradually mixes with the cooler water. effectively sort of becomes cooler water and begins to descend back down. And so what we've got here, in addition to showing you convection itself, we've got what are known as convection cells. A convection cell is a complete loop in which heated fluid rises spontaneously because of the buoyant force, and it descends spontaneously also because of the buoyant force. That basically the fluid gets too heavy, too dense to be supported, and it goes down and flows back through the heating element. So it loops. If we put a drop of ink in here for a short period of time, you'd be able to watch the ink rise and then descend and then perhaps rise again. And pretty soon it would get messed up because there's a lot of complicated structure in that rising portion. Is that okay? Yeah. Where do the air bubbles come from? I think those air bubbles, which you see growing right here, they're actually growing on the surface of that element. They are either air coming out of solution in the water. We'll talk about water dissolves gases, but it dissolves them better at cold temperature than it does at warm temperature. So that's either air coming out of solution, which is an interesting part. You've seen this on pots. When you start cooking water on the stove, early on, you start seeing bubbles form in the bottom, deep in the water on the edges. Where are those coming from? That's the air coming out. That's what the fish breathe that, right? That's part of life for fish and aquatic animals. But it does dramatically reduce as you get hotter. The other possibility is, because this is electrically heated, there's an electric difference. It's like a battery from one side to the other, and we could be breaking up water molecules into its constituents, oxygen and hydrogen, which is fun to do, particularly if you light them after they're done. I can't remember whether we'll be doing that or not. I might do that. The right mixture of oxygen and hydrogen, once you've created it by taking apart the water molecules electrically, when you light them to go back, it's pretty dramatic. It's not like the Hindenburg, which just burned simply. It's kabang and startlingly loud. Other questions? All right. Sorry, you're being dazzled here. All right. So that's convection, and a more complete name for it would be natural convection. Now I can turn the lights back on, maybe. What? Yeah, pretty good. Okay, would be natural convection. Natural convection takes place in your oven as well when you turn on the lower heating element. So this is just, when you turn on the lower heating element of an electric oven, which many of them are, it's just like this. A hot filament, heated electrically, warms a fluid. In the oven, it's not water anymore, it's air. And the air rises, goes up to the top, and spreads out, and comes back down to pick up heat again. So that's what you get in an oven. What did I want to say with this? Oh, that's normal convection. So-called convection ovens are actually forced convection. They omitted the word convection oven. Well, all ovens are convection ovens. What's missing is the word forced. They have a fan that moves the air, whether it's heated and whether there's a buoyant force or not. So convection ovens, it's misnomer. It should be forced convection. Yes, Savannah? When well, yes, the question is people talk about heat rises, and what that is super shorthand for is heated air rises. That's true. And up it goes, and it conveys heat to things above it, and as it does give up that heat to the things above it, its temperature drops. And when it drops, it's no longer buoyant. That is, it's no longer lighter than the surrounding air, and so it tends to come back down. So that completes the convection cell. If the air rises and nothing replaces it, you're going to get low pressure down below, and that area won't be able to support the column of air overhead. So it has to be replaced. So that's the descending part of it. Is that getting the question? Would you be able to feel the temperature difference? Yes, because that column of rising hot air can be considerably hotter than the surrounding air. And so this is totally relevant to the wood stove. If you take your hand and pass it from not over the wood stove to over the wood stove to not, when you're over the wood stove, you will know it. You'll feel a wind of hot air rising off of it. It's only a question of how hot, and you can burn yourself doing this. The same thing over a fire, or a burner on a stove. As you go over the stove, you'll feel that rising air as a tremendous flow of heat. Actually, flames. Think of this. Flames take their structure. The flames that you're used to. This flame, right there, that takes its structure from hot air rising. If you turned off the buoyant force, the candle wouldn't burn right. And they've played with this in say manned space, but human space. The astronauts have played with what is it like to light essentially a candle when there's no buoyant force. They're actually in free fall. I hope you now realize they're not free of gravity, but they can't sense gravity because they're falling. The same thing happens for a candle. If you get rid of gravity, and we have demonstrations where if you light a candle, put it in a container and drop it, the candle goes out. Not because a wind blows the candle out, but because it has no buoyant force to lift the burn gas away to be replaced by nice, lovely, fresh oxygen. The ball of burn gas just stays there and stifles, smothers the flame. So you can't have a romantic dinner on a spacecraft with no gravity. You need electric candles or something. Boring. Okay? Relevant to wood stove, convection definitely does take the heat. Tremendous amount of heat comes off the stove, goes right to the ceiling. And it'll spread out in the ceiling, warming the ceiling nicely. The cooled air will eventually come back down, but if you've got some great room in your ski lodge that's heated by a wood stove, and you're not likely to be living on the ceiling, you're living down here where most people walk, you want to take that heated air that's going to accumulate up there and bring it down. And you do that by forced convection. You have a ceiling fan. So a value of having ceiling fans associated with wood stoves is to bring the heated air down to the living level of the house, of the room. Is that okay? So I guess wood stoves and ceiling fans go together like this. What else? I guess that does it. All right. One other observation about convection is, what if you heat the top of a fluid? Will natural convection carry heat to the bottom of the fluid? Do you understand the idea? So instead of heating down low on the ground with a wood stove, what if you put the wood stove on the ceiling? Will you get significant hot air down low? How many think yes? How many think no? No's have it. No's right. So I can make it so you can see it. Let me turn the side projector back on. Center projector. My chances of remembering to undo this are 0, so tell me when I forget. Okay. So what I'm going to do, I've got a test tube of water, and if I hold the top and I heat the bottom, I am going to burn my fingers, because I will make hot water, which will rise up, transfer its heat to my fingers, and then go back down for more. And very quickly, I will be unhappy. So I'm not going to do that. I'm instead going to hold the bottom of the test tube and heat the top. Hopefully you can see it's boiling frantically here, and I haven't noticed a thing. And it's not just because I'm a clueless physicist, although some would argue otherwise. So no problem. You can heat the top of a fluid and be safe from convection. at least natural convection. If you force the convection, if you put a stirrer in there and shove the hot water, if I grab it here, I'll burn my fingers. It's hot up there, cold down here, but they just don't, natural buoyancy isn't going to exchange them. Forced convection is another matter. You gotta be careful not to touch the top. All right? Yeah. Thanks. Okay. I mean, just to point out, in a case where this applies, is if you are cooking in a stove and you don't heat the bottom of the air with the bottom element of a stove, those of you who have spent much time cooking in an electric stove in particular, know that it has two heating elements, most likely, one at the bottom and one at the top. If you turn on the top element only, it heats the air at the top of the stove, top of the oven, and no convection occurs, assuming you don't turn on the fan of a convection oven. In that case, if you put your brownies or whatever in there, or cookies in there to cook in hot air, you'll be disappointed because there won't be much hot air coming down to get them. The cooking will take place entirely through a different heat transfer mechanism. It won't involve conduction because the cookies aren't touching the heating element. It won't involve convection because natural convection doesn't work when you heat the top and try to convey heat to the bottom. It goes by way of the third heat transfer mechanism, radiation, and that's the story here. So about radiation, a little background on what is an electromagnetic wave. Electromagnetic waves are something I do in depth in the spring course, but as a basic rule of thumb, they consist only of electric and magnetic fields, which that passes the buck. What's an electric and magnetic field? An electric field is a structure in space that exerts force on charged particles. And a magnetic field is a structure in space that exerts force on magnetic particles. In electromagnetic wave, those two things, which they have a reality, I mean, you can't see them, you detect them with charges and magnets, but they have a reality, they're really there, and they can carry energy, they actually carry energy and momentum, the whole trick, and they do it without passing through anything except the space itself. So it's kind of got a mysterious element to it, but it is what it is. The electric and magnetic fields work together as a team to keep themselves going, and they whiz off at the famous speed of light forever, until something absorbs them or reflects them or something. They're off and they'll travel across the universe. So to create or receive an electric or electromagnetic wave, the simplest way to transmit an electromagnetic wave is to jiggle a charged particle. So it turns out any time a charged particle accelerates, it will emit an electromagnetic wave, or more than one. So if you take a charged particle, the familiar charge of static electricity, and suppose you got static electricity on your hands. If you shake your hands up and down, you are emitting electromagnetic waves. They head off, they carry energy away from you, and so on. If you look more at tiny particles, if you just look at some object that's hot, or even pick any temperature that's not absolute zero, so my skin here, for example, the skin contains charged particles. Atoms and molecules are built out of those charged particles, and they have thermal energy, so they're jiggling around in various ways. They can emit electromagnetic waves because they're accelerating. So you got accelerating charged particles. They can emit electromagnetic waves. The hotter the surface is, the faster its electric particles, electrically charged particles, are jiggling, the higher the frequencies of the waves it emits. Frequency is the measure of how many times a wave goes through its motion every second. So if you watch a passing water wave that's coming by up and down, that frequency might be one cycle every couple of seconds. It's a very low frequency. For the waves that come out of a radio transmitter, they may be a million cycles a second, or even tens or hundreds of millions of cycles per second. For the waves that come off of things in this room at room temperature, because of that thermal motion, the frequencies of these waves are more like 10 to the 13 or 10 to the 14 cycles per second. That means something to do with it. You know, a trillion cycles per second, very many, 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 many cycles per second. Details don't matter, but they are coming off, and they go off, and they zip through empty space or through air. That doesn't bother them pretty much. And when they arrive at something else, another charged particle, the other charged particle can be jiggled by them. So they can convey thermal energy from one place to another. The original place emits one of these thermal radiation waves, and the receiver absorbs it. It comes on and it jiggles the charged particles in that receiving part, and the energy is conveyed. You're okay with that, or questions about that idea? That surfaces just send electromagnetic waves off and receive them all the time. This is true of all the surfaces in this room. They're all emitting thermal radiation by virtue of the jiggling charges and the thermal energy that they have. And they're all of them absorbing that energy as well. So it's coming and going all over the place. The hotter a hotter surface is, the higher the frequencies of the waves that it emits, and the brighter it becomes, the more of those waves it becomes. And it becomes brighter surprisingly, it depends surprisingly strongly on temperature. Do I have that as the next slide? Yes. The emission of thermal radiation by a surface depends on things like how much surface you've got. It basically scales with the amount of surface. But the more important thing is the power, that is the joules of energy per second, or watts, that come off of a surface depends on what? Something called emissivity, which I'll come back to in a second, a constant of nature known as Stefan Boltzmann's constant, the temperature to the fourth power, where temperature is measured on an absolute scale, where 0 is the real 0. And finally, surface area, that is how much surface is emitting this glow of thermal radiation. So let's just look at all these pieces. I'll start with surface area. Obviously, the bigger a surface is, the more opportunity it has to emit thermal radiation. So it shouldn't be surprising that if you double the surface area, you double the thermal radiation. Hope that's okay. Stefan Boltzmann's constant is just a constant of nature. That shouldn't be a big surprise that you need some relationship that sort of sets the scale of everything. Temperature to the fourth power, I'll do that one next. This says that if you take the temperature of this room, which on an absolute temperature scale, the Kelvin scale, the temperature of this room is about 300 Kelvin, give or take a little bit. If you go, so a surface at room temperature is emitting a certain amount of thermal radiation. Believe it or not, it's there. If you double its temperature on that Kelvin scale, which means to heat it up to about 300 Celsius, 600 Kelvin, which is about 300 Celsius, or about 450, 470 or something like that Fahrenheit, it will emit not twice as much thermal radiation, it will emit 16 times as much. It goes up hugely with temperature, very dramatically, with small increases in temperature. That temperature of the fourth power is a big deal. Last thing here is emissivity. This is how well a surface interacts with electromagnetic waves. How good is it at emitting them and absorbing them? And you know, you're familiar with what colored surface is the best at absorbing thermal radiation, at receiving it. Black surfaces, their definition is a surface that absorbs all electromagnetic waves that come at it. It turns out black surfaces are not only good at absorbing thermal radiation, but emitting it as well. So a black surface, and that's what I've got here. So now to sort of do the demonstration part of this, before I totally run out of time. This box here is heated by a light bulb. There's just an old-fashioned incandescent light bulb in there. So it's just, it's not horribly hot. You know, it's hot, but not bad. So that surface looks to your eyes as black. That means that any light that hits it never comes out. completely lost and absorbed into it. It's got a beautiful response to an incoming electromagnetic wave. That electromagnetic wave jiggles charged particles in that surface, and they just gobble up the wave. But the same result, good absorption, it means good emission. This surface is excellent at emitting its own thermal radiation. So it is not black in the sense that no light comes out of it. It's black in the sense that it absorbs anything that hits it. But it is capable of emitting thermal radiation very well, basically perfectly well. That emissivity idea here, the value of emissivity goes from 0 to 1, where 1 is black, perfect ability to emit and absorb thermal radiation. And so this is an emissivity 1 surface. As a result, when I take that heated surface with emissivity 1 and use a device that stares at it and says, how much thermal radiation is coming at me? The answer is lots. That bar graph is showing us that it's seeing a lot of thermal radiation. I can block the thermal radiation just with a sheet of paper. So I've blocked it. What the measuring device is now seeing is the thermal radiation coming off of a white sheet of paper at room temperature. And that's not very much thermal radiation. So I'll let it see the black again. Okay, so the thermal radiation is real. What I have, you can play with these. Come up and play with these. I would have sent them around. These are just little devices that see thermal radiation and report the temperature they see. They can tell by the character of the glow what temperature they're staring at. So this guy's, it's my hand, it's seeing 82 Fahrenheit. You know, my ear, 94-ish. It just looks at the incoming thermal radiation and tells you the temperature of what it's looking at. So they're very useful devices. You've seen these in doctors' offices, whatever. They come, when they're blasting you in the ear, they're not actually, they're just looking for the thermal radiation coming out of deep inside your ear, which is pretty much core body temperature. Okay, so a little bit more about this, and then I'll stop. So this is emissivity 1, black surface. If I take a metallic surface, here's the shiny surface. This one is mirrored. This one sends very little thermal radiation at that measuring device. Why? Because it's reflective. Instead of black objects have emissivity 1. Truly reflective, transparent, or white objects have emissivity 0 in principle. That is, they don't tell you their temperature by way of thermal radiation. They either reflect your own thermal radiation back at you, or they send it through from behind. I'll talk more about those guys another day. But so the shiny surface sends very little thermal radiation because it's got emissivity of 0. The black one sends good. What I'm going to do is I'm going to use thermal radiation to ignite a match. There's a match over here. So the way we can finish the day is there's a match over there. See the match up there? That's right here. Okay? We can light the match by sending thermal radiation at it from a hot filament over here. So when I turn this filament on, we're now sending thermal radiation over at that match. And heat is flowing from hot to cold and lighting the match. Or burning it up anyhow. There we go. Match lit. Yay. Now it doesn't know how to focus. All right, so that was thermal transfer, heat transfer from hot to cold by way of radiation, electromagnetic waves going right through empty space.